so that I can convert my recording to a video file, and then I will continue. So I'll let you know whenever I stop. Okay, so we'll continue with this module on IP protocol. So we saw fragmentation in detail previously. So now we'll continue with some what's called auxiliary protocols. So auxiliary protocols are something that will kind of be an addition to the main IP protocol. Okay. So we'll see a couple of them. The first is the address resolution protocol. So the purpose of address resolution protocol is called ARP, as the name itself indicates, is to resolve an address. So it resolves the IP address of a host to find its MAC address or hardware address, you can call link level address. So the problem is this: so if a router or any host in the network wants to send a unicast message to another host in the same network, and let us say the sending entity, the router or the host, doesn't know the MAC address of the destination host, but it knows its IP address. So the sending host can, before it can send the unicast packet, because it doesn't know the MAC address of the receiver, it can broadcast what is called an ARP request message to everyone in the network. So to do this, the destination IP address has to be a broadcast address, and in the ARP request message, the sending host will specify the IP address of the well, let me take it back. So to do this, the sending host has to do a broadcast at the hardware level. So the destination broadcast address at the MAC layer will be the hardware broadcast address, which will be all ff.ff.ff and so on, the 48 bits. And the receiving host IP address will be the IP address that it's looking for. Okay, so everyone will get it because it's a hardware broadcast, but the message is really meant for the host whose MAC address the sender wanted to find. So the intended host will only process this message, and it will reply with an ARP reply message telling this is its hardware address or MAC address. So the sending unit will then learn the MAC address of the receiving host, and it will store this address in its what's called the ARP cache or the ARP table. Now, so from there, whenever it wants to send a unicast message to that particular host, it will use the MAC address that it is now in the ARP cache. Now, the other hosts in the network which received this ARP request, which is a broadcast message, they will learn the sending unit's MAC address as part of this broadcast. So everyone gets the broadcast from the sending unit, so they will get to know the hardware address of the sending unit, and they'll also update the ARP cache with a mapping telling this is the IP address and this is the corresponding MAC address of the sending unit. So this way every host will be able to update the ARP cache with some information. Okay. So using this public chat feature, you all can type and ask me any questions if you have in between, and I can answer that question for everyone. Okay, so the next protocol is this dynamic host configuration protocol. It is called the DHCP protocol. Now the purpose of this protocol, as you may know by now, that the machines that you have in the lab, the computer lab and all these machines, they don't have a dedicated IP address. So each time a machine boots up, it may get a different IP address. Okay. Whereas if you look about the servers, like the web servers and file servers that are running out there, the server machines need to have a dedicated IP address. So even if you reboot the server, it will have the same IP address. So what is going on is this. So as you know, also from the first module, the IP addresses are very limited. The public IP addresses especially are very limited. So if you put all your machines in a lab and they are in a public network, we cannot have a dedicated public IP address for every machine in the lab, because not all machines in the lab are going to be used or running all the time. So a machine needs an IP address only when it is running, and when it is not running, it doesn't need an IP address, especially from the those things that are at the client side and the lab side. So whenever a machine boots up, it doesn't have an IP address. So when a machine boots up, it has to request for a public IP address from what is called the DHCP server. So when it boots up, it has a kind of what is called a startup address called 0.0.0.0. So that is the IP address of a machine when it boots up. And it requests what is called by sending a DHCP request message to, DHCP discover message to all the hosts in the network with a targeted IP address. It's a broadcast to all machines within that network. So only the DHCP server, so there's a DHCP server that's going to run in each network, and this is a machine server that is going to allocate an IP address to that requesting host. And the DHCP server is going to have a pool of available IP addresses, and it's going to keep track of like what are the IP addresses that it has assigned and what are still available to be assigned and so on. So it's like on a lease basis. So the server can allocate the IP address for every day or every week or something, depending on how the administrator has set it up. So it will send a reply back to the requesting machine, because the requesting machine would also send its MAC address as part of the DHCP discover message. So the server will be able to respond back to the specific requesting machine only with an IP address. So if the requesting machine is still requiring an IP address after the lease is expiring, it can again send a DHCP discover message, or it can renew the lease and keep the same IP address, or the server could allocate it a different IP address when the lease expires and a new lease needs to be established. So the message is the client machines, especially in non-server environment like in a lab, student lab and so on, they don't have a dedicated public IP address. It could change depending on the day and depending on every time you boot it up and things like that. So one student is saying he cannot hear me. I think everyone else can hear me, isn't it? Did you turn on your microphone?
I can hear you just fine.
Oh, okay, thank you. So Darren, did you turn on your microphone? Alright, everybody else is able to hear me, so please figure it out. Okay. Okay, so the next protocol is actually a suite of protocols here. It's called the Internet Control Message Protocol, or ICMP. So it can be used to give some feedback to the sending source if there are some error messages or something erroneous happens to the message that is being transmitted. So typically the routers use this protocol. So if a router wants to send some feedback back to the source, it can use this protocol. And it can also be used to send some control messages to improve network performance. So let us see one by one. Okay. So the ICMP messages, even though they are for reporting some error and doing some performance issues, performance monitoring, they don't have any priority. They are still forwarded by the routers the same priority like any regular IP datagram. Okay, so we already saw several of these issues. For example, if a router doesn't know how to forward a packet, so we saw in the earlier module, how does a router decide the next hop. So if a router does all that work, like the bitwise and operation and all this stuff, and is still not able to figure out what is the next hop for a particular packet, then it has to simply drop that packet. So it does that, and it does drop the packet, but also will tell the source that the destination is not reachable. So it will send an ICMP error request message by informing that. So each of these error messages have a code. Okay, so this is how the ICMP packet will look like. So the IP datagram has IP header and the payload, the data portion of the IP header datagram. So the payload is now going to have the ICMP information. So it will have an ICMP header. So the IP header, typically after the IP header you will have the transport layer header, the TCP header or the UDP header. But remember, in the IP header field there is one field called the next protocol field. So the next protocol field will have an 8-bit field. It will have a code for each of the protocols that can be used as the next protocol. So if you want to include send an ICMP message instead of a regular data packet with a TCP header or UDP header, you can include in the IP header next protocol field a particular code that will correspond to an ICMP message. So include that in the IP header. That means then the router will know after the IP header it has to look for the ICMP header. So in the ICMP header you can include the code for what type of ICMP message you are sending. So it could be any of these, and these are the corresponding code values. And you could have some payload also in the ICMP unit of information. So you could we'll see one by one where can you use a payload. Okay, so the first thing we'll look at is the destination unreachable. So if a router doesn't know how to forward a datagram, it can drop the datagram and inform the source accordingly by sending the code 3 in the ICMP header indicating the destination is unreachable for the source. Next one, it could be used for when the TTL reaches 0. You also know every router will decrement the time to leave TTL field in the IP header. So if a router decrements the TTL field and it reaches 0, that means the router should not forward the datagram further. So the router will again drop that datagram and inform the source that the TTL reached 0. So that is corresponding to time exceeded field. Okay, so that is like the code 11 used in ICMP header. Now the checksum failed. So also the routers will compute the checksum on the different field values in the ICMP header, and if during transmission some erroneous some bits change, then the receiving router, when it recomputes the checksum value will not match with what is in the IP header. So the router will again drop the packet and tell the source that the checksum doesn't match, and that will correspond to the parameter problem, or IP header is not right. Okay. Then the cannot fragment. So we also saw in the fragmentation topic that there's a DF bit in the IP header as part of the flag field. So if the sender source sets the DF bit, that means do not fragment. So any router will not be able to fragment the datagram if the datagram needs to be fragmented before it can be forwarded further. So again the router will drop the datagram and inform the source that it could not fragment the packet. So there is a code for that. This is why it's only a subset. So there are a lot of codes. You see, the numbers are not continuous. So if a packet has to be dropped due to the fragmentation cannot fragment problem, there will be a separate another code for this. I didn't list all the code, but if you just Google ICMP, and you can see all the code values for the different error messages. Now sometimes you could also send what is called ICMP redirect. That means the router will forward a packet based on the destination IP address. And when a router figures out that typically also the packets are sent on the shortest path. So when a router figures out that it is not on the shortest path from the source to a destination, then the router will would like to tell the source that it is not on the shortest path, and it could change the route if needed. So that way the source can redirect the packets on the shortest path to the destination. So in order to tell that to the source, there is the ICMP message available, and that can be made use of by a router. Now the last thing is what is more commonly used as part of ICMP. It is called the echo request reply. So some of you might have tried this ping command. So if you want to know where typically where server is on or running, on or not, then you can ping, just say ping, and then type the IP address of the server or even the website address www.jsums.edu. Then if the server is running, it could reply back. So that's called the echo request reply. So this is where in the payload you could put some dummy message, whatever the message you could want to send in the echo request. So typically you send 4 echo request messages for each time you run the ping program. And the other side, the machine that you are really testing, will respond back with an echo reply with the same dummy message that you sent in the request. So that way you can authenticate the server that it is a server that is responding back, because it has to echo back the same message that you included in the echo request. So the server will send back the reply. It's called the echo reply with the same message. That way you can, if you get back the reply within a certain time, then it means the server is up and running. If you don't get back a reply within a certain time and you time out, that's when you decide the server is not running. So that is a very useful command that you can use for testing whether some destination machine is alive, running or not. Now it could turn out to be a security issue, and it did turn out to be a security issue several years back. So some administrators for the server machines, they do not let their machines to send back a reply. So they just so the echo request messages could just get dropped when they reach the destination network. Because as a security attack, someone could launch a series of ping echo request messages to a server, and all the server will then do is just keep on sending echo reply messages. So Darren, what are you doing? Can you hear me? Okay. So that way the server machine will quickly run out of memory, because it has to keep track of all the request messages it is receiving and then keep replying for every requesting unit. So so this is like a denial of service attack. The server cannot do any other useful job. So because of the security issue, a lot of server machines are now disabling the ping echo request command. Okay, but it's a very useful command to test whether some machine is alive, running or not. Okay, so let me stop for a minute and convert this recording to a video, and then we'll be back in a minute.